So here we're learning about this idea called limiting reactants on pages 7 and 8. And make sure that you have a periodic table and a calculator nearby, because I am going to leave you a little bit of that last problem on page 8 to do on your own. But there are 4 examples between here and there, so I think by the time we get there, you'll really understand what I need you to do. So, what is a limiting reactant anyway? Well, the definition is the reactant that determines the amount of product formed in a chemical reaction, which means this is the substance that's used up first and makes less. We've talked about chemical reactions being like recipes, and we don't always mix things in quite the perfect amounts so that they make a perfect recipe. We might have more of one thing than another. And so, just like if you're making pancakes and you have 15 cups of flour, but you only have 3 eggs, the eggs are going to be running out before the flour. So the eggs would be our limiting reactant. The excess reactant is the one that is not completely used up. It's the one that has some left over when the reaction is done. So in that case, that would be our flour or baking mix there, because I had plenty of it to make all of the pancakes that I want and some left over. Now, if we used all the pancake mix, it would make more pancakes. But since the eggs run out first, those wouldn't really be real pancakes that we could make from it. That's just kind of imaginary, wishful thinking pancakes. So when we're solving these stoichiometry problems, we're going to end up getting 2 answers out of them, because we're given 2 different amounts of 2 different substances. So we're going to use those to work 2 problems, but the smaller answer is always going to be our real answer, because that bigger answer is not actually possible when we mix those 2 things together. This limiting reactant is the one that's going to determine how much stuff we can make, because it runs out first. It makes the smaller number of pancakes. So, how can I tell that something is a limiting reactant problem? Well, there's going to be 2 givens telling you the amounts of both reactants being mixed together, and the problem's going to ask you to find the amount of a product. So, here's an example. It says that a 16.2 gram piece of aluminum reacts with 61 grams of hydrochloric acid. So those are 2 numbers given to you, and it's talking about aluminum reacting with hydrochloric acid, those amounts of both of those things. And then someplace it says how many grams of gas are produced. So it's asking you, how much stuff do we make if I mix this stuff together? That's a limiting reactant problem. In contrast, a normal stoichiometry problem normally just has 1 number in it. It's 22.8 grams of NaOH. It's the only given. You can tell this is just going to be 1 stoichiometry problem for you to do. And all it is asking you how many grams of water are formed. Sometimes even it mentions that other substance. It says that that much sodium hydroxide is reacted with hydrochloric acid. And sometimes it might even say reacted with excess hydrochloric acid. So this is telling you in the problem, don't worry about the amount of hydrochloric acid. There's going to be plenty of it. Evidently, the sodium hydroxide is the limiting reactant. It's going to run out first. So this isn't a limiting reactant problem because they haven't given you both of those amounts. They've kind of made that choice for you and only given you the number that is actually going to give you the answer. And then finally, percent yield problems can sometimes seem like limiting reactant problems because they will have 2 givens in them. But if you notice, this is telling you that 2.25 grams of sodium chloride reacts with some silver nitrate, and then this 3.45 grams of precipitate is formed. So it's telling you how much stuff was reacting and how much stuff you actually made. This is our actual yield, which we will need to find our percent yield. Also, percent yield questions have to ask you to find the percent yield in them, so they kind of label themselves. So there shouldn't be any huge confusion about them. There's never going to be any problems that are limiting reactant and percent yield problems at the same time. You're always going to have some very separate pieces given to you, very separate information. So these are the only 3 types of problems we're going to be working out this unit. So let's go ahead and look at the process for solving these problems. Now, this looks a little bit different than what's in your packet, but this, I think, is a little bit simpler and more straightforward. The packet has a little bit more information in it, but I know that sometimes too much information can get confusing and just wordy, and you don't want to read that. So this is my simple steps. And I'll kind of show you how to edit your packet in just a moment to make it kind of get the information you need from here. You can also just write this off on a Post-it note or something separate and slap it on top of it. Or when you come to class next time, I can give you a copy of these steps so that you can just glue or tape that in over the top. But just make sure that you have the right processes down no matter which ones they are. So once you realize you have a limiting reactant problem because you have two givens to start off your reaction, you're going to set up and solve two stoichiometry problems. Start them with those two givens that you've got, and you're going to be ending at the same product, the same unit, same product. So there's going to be some similarity between some of these numbers you need to use. And then of those two answers you get from your two stoich problems, the smaller one is your real answer. That's the one that needs to have the unit and substance on it, and either circle it or box it so that I know that that is the answer that you think is correct. If you just give me two answers, you won't get credit for either of them being your final answer. I'm not supposed to be choosing between them, you are. And if you're asked to identify what the limiting reactant is, then the given that gave you that smaller answer is your limiting reactant. So just follow that final answer back to the given, and that is what your limiting reactant was. Now, some problems don't ask you to find how much excess reactant is left over, but if they do, it's really just going to start from the limiting reactant again. So it's really important that you do those first two steps. As you notice here, this is a 4-step process in total to finding that excess reactant, but it is always going to start with you finding the limiting reactant first. And once we know what the limiting reactant is, what we're doing here in these third and fourth steps is just figuring out how much excess reactant got used up while the limiting reactant was getting used up. So that after we figure out how much of it got used, and we knew how much we started with, we can subtract the two, figure out how much we were given minus used, tells us how much is left over. Now, this is going to mean one more stoichiometry problem if you're asked to find how much excess reactant is left over, but that stoich problem is just going to start with the limiting reactant as your given, so you're starting from one of your givens that you already started a problem with earlier, but this time you're going to end at the amount of your excess reactant, and you should aim to probably have the same units that you were given so that you can do this subtraction later. And that's all you got to do. Go from one reactant to the other, find that answer that tells you how much got used, then take given minus used, and that tells you how much is left over. So let's get those steps on the page to match what I just said, if you're not planning on getting that paper from me or just writing out those other steps someplace else. This looks like 3 steps, but this first step really is kind of just get ready to do stoichiometry. You need a balanced chemical equation, and you need to have those 2 givens for those 2 reactants to be able to do the 2 problems that we're about to. But step 2 is really where you start doing stuff and solving the problem. So you're going to be setting up and solving 2-dimensional analysis problems. I would recommend that you add this little note reminding you of how to set those up. You're starting with your 2 givens, but you're going to the same product, whichever product it's asking you for. And then once you solve your 2 problems, the smaller amount of product is your real answer. And the smaller amount of product came from that limiting reactant so that you can find that. But you need to make sure that you identify your real answer. So that's our limiting reactant problems. If we are asked for excess reactant, then of course we're going to have to work from limiting reactant to excess reactant, like I said. This just kind of sets the stage after you've done this other stuff, but of course we'd have to do that first. That tells you how much excess reactant was used, and then we are going to be subtracting like it says in step 3, but it actually has that backwards, so I'd like you to cross that out, and then just write given minus used equals leftover. So we always have the given amount of that excess reactant. It's in the problem. You just need to calculate that amount used using one more Stoich problem, and then you can do the subtraction to find the leftover, or the remaining excess reactant. So that should be good enough, but if you want those steps that I gave you, I do think it's a little bit simpler, but to each their own. You choose. Let me know what I can do to help you. So let's look at an example here. Here it tells us that 6 moles of barium chloride are placed in 5 moles of H2SO4. So that's the reaction we see down here, which luckily is pretty simple to balance, just a 2 there at the end. Wants us to figure out how many moles of precipitate will be formed, and I'll tell you a little bit later how to predict what the precipitate is going to be, but for right now, just imagine that asks you for how many moles of barium sulfate will be formed. And, of course, how much excess reactant remains after completion. So, we're just going to start from that first given that I see, moles of barium chloride, and this is going to be a 1-to-1 ratio to convert from barium chloride to barium sulfate, and that tells me that if all the barium chloride is used, then that will make 6 moles of barium sulfate, but I have another given to use, so I have another problem to set up, still a 1-to-1 ratio. So from those 5 moles of sulfuric acid, I could make 5 moles of barium sulfate. I have 2 answers. Which one is my real one? My real final answer is always the smaller one. So 5 moles of barium sulfate would be formed from that reaction. That's our answer. And if we follow that back, H2SO4 is the reactant that gave us that answer. So that is our limiting reactant. That's also going to be our starting point in figuring out how much excess reactant is remaining. We take those 5 moles of H2SO4, use that 1-to-1 ratio to find how much barium chloride got used when we reacted 5 moles of H2SO4. Unsurprisingly, that's 5 moles. And since we started with 6, 6 minus 5 means there's 1 mole remaining. Not too complicated, and you might have been able to predict that if I had less H2SO4, it was going to be the limiting reactant. But that's mostly because this was a simple mole-to-mole problem with a really simple balanced equation. These next few are going to step it up little by little, but the process is still the same. Here, we're mixing equal amounts of aluminum and oxygen, and this is a synthesis reaction here, 4-3-2 when it's balanced. If we start with those 3 moles of aluminum, that would be making 1.5 moles of our aluminum oxide, and with 3 moles of oxygen, because that's a 3-to-2 ratio, we could make 2 moles of aluminum oxide. So even though I put in equal amounts, because my balanced chemical equation needs more aluminum for each time this reaction happens, the aluminum ran out first. So our smaller answer is still our final answer, making sure we got our number unit substance all together in that final answer. This also means that aluminum is our limiting reactant, like it was asking us to identify. And if I use those 3 moles of aluminum, I can calculate how much oxygen got used up when reacting with that aluminum. It's technically 2.25, but I rounded that to 2 sig figs here, so 2.3 moles of oxygen got used. When I subtract 3 minus 2.3, that means 0.7 moles were remaining. In question number 3, we have a kind of complicated reaction to balance, but I'm helping you out here. We've got 9 moles of ammonia heated with 10 moles of oxygen. But just keep using these mole ratios from our balanced equation. It's asking how many moles of our NO is made. So we're going to be starting off with this 4-to-4 ratio, telling us if all of that ammonia is used up, it'll make 9 moles of NO. We have 10 moles of oxygen, which seems like, okay, more oxygen than ammonia, but because of this 5-to-4 ratio, we can only make 8 moles of NO with that, which means that even though it technically was the larger amount, oxygen was our limiting reactant here. So don't just think that it's always going to be the smaller amount of the reactant. You've got to do the math and choose the smaller answer, and that smaller answer is the one that's going to be coming from the limiting reactant. But same process as before, 10 moles of O2, work backwards or kind of sideways to the moles of ammonia that got used up. That would be 8 moles there. Since we started with 9 and only used 8, there would be 1 mole of our NH3 remaining. So these first 3 problems have been mole-to-mole problems to help you see this process and understand some of the variations that can happen with these problems without making the stoichiometry too complicated. But we can introduce mass into this process. The rest of the process is still the same. It's just a little bit longer stoichiometry problem, but you still do 2 of them and choose the smaller answer. I am going to take out a little bit of mass from this problem there in part B. If you just change that to moles, kind of makes more sense because they were given to you in moles, but that's just my opinion. We'll work another example in the next example will be all mass. So here we want to find the mass of our product from 5 moles of iron and 6 moles of oxygen. So that 5 moles of iron, we're just going to start by going 4-to-2 ratio. And this is where we stopped before, but because it wants the mass of that product, then I'm going to go add up Fe2 and O3 from the periodic table, which equals 159.689 grams. That's just one more little step here. Multiply and divide to get our answer. And if all of that iron's used up, I could get 399 grams of product. And even though I have a completely another stoichiometry problem to do, we still just use that simple ratio from our balanced equation first. And since we're still going to grams of iron oxide, it's still the same molar mass here. So it's an extra step, but it's the same step for both. So it's not actually quite as hard as doing 2 completely separate problems here. So if all of the oxygen gets used up, then that could make 639 grams of iron oxide, which means 399 is our answer. Of course, needs number, unit, substance. And that means that our iron is our limiting reactant. And if I want to find moles of our excess reactant, moles of our oxygen, I just have to use a simple mole ratio to go from moles of one to moles of the other. And then that tells me how much got used, and I can subtract to figure out how much is remaining. So, hopefully not too bad. Now, this last problem is all grams in it, but the good news is it didn't ask for you to find how much excess is left over. So that is going to simplify things a little bit. Let's go ahead and balance this equation. And I told you I was going to have you do part of this one. So I'm actually going to leave you the aluminum reaction to set up and work out the stoichiometry part of that. I am going to start with the 61 grams of HCl. Turn those grams into moles using the molar mass of HCl, just H plus Cl. And remember that the opposite side of our grams is always 1 mole of the same substance. Now that I've got moles of HCl, I can use my mole ratio from my balanced equation to find my moles of gas, and hydrogen will be the gas that we care about here. Aluminum chloride is not a gas. So we're going to use that 6-to-3 ratio here, and that would get me moles of hydrogen, but I want grams of this gas. So I'm going to have to add up the molar mass of H2, which is just 2.016 grams. So this is where I'm going to tap out and leave you to finish this answer and set up and work out the aluminum problem on your own. Will not stamp your packet unless you get this answer correct. And I don't want to see two answers. I very clearly want to see one boxed circled answer as your final answer here for that stamp. So, not that you need to, but on the next page, this is what I plan on starting with next class. It's another gram-to-gram limiting reactant problem. It just looks a little different because each of those parts and those things that are being asked for separately. And then we shoved a little percent yield problem there on the end of it. So I'm going to work this in class, but this is probably the biggest, most complicated type of problem that we're going to work out this unit. So if you can try this out and get it right before you even come to class, you can check that answer with me or my packet when you get there. And if you got it right, there's literally nothing you can't do in this packet. You can finish that up with confidence without too much help from me. So consider giving it a try, coming into class ahead of time if you can't and want help. But that's it for this podcast. I'll see you in class.